I'm Jemuel Naldi Malyari from BSTPE 4A. I'm discussing uh, all about SAP1 or simple as possible computer. Details of functional components of a digital computer. CPU, input, follow arithmetic, logical unit, CU or control unit, MU or memory unit, and output. Next, I will discuss each component, how the functional components fetch or process. In input unit, the input unit consists of input devices that are attached to the computer. These devices take unit input and convert it into binary language that the computer understands. Some of the common input devices are keyboard, mouse, joystick, scanner, and etc. In central processing unit or CPU, once the information is entered into the computer by the input device, the processor processes it. The CPU is called the brain of the computer because it is the control center of the computer. It first fetches instructions from memory and then interprets them so as to know what is to be done. If required, data is fetched from memory or input device. Thereafter, CPU executes or performs the required computation and then either stores the output or displays on the output device. The CPU has three main components which are responsible for different functions. It has arithmetic logic unit or ALU, control unit or CU, and memory registers. In arithmetic and logic unit or ALU, the ALU, as its name suggests, performs mathematical calculations and take logical decisions. Arithmetic calculations include addition, subtraction, multiplication, and division. Logical decisions involve comparison of two data items to see which one is larger or smaller or equal. In control unit, the control unit coordinates and controls the data flow in and out of CPU and also controls all the operations of ALU, memory registers, and also input and output units. It is also responsible for carrying out all the instructions stored in the program. It decodes the fetch instruction, interprets it, and sends control signals to input and output devices until the required operation is done properly by ALU and memory. Next is memory registers. A register is a temporary unit of memory in the CPU. These are used to store the data which is directly used by the processor. Registers can be of different sizes. It has 16-bit, 32-bit, 64-bit, and so on. And each register inside the CPU has a specific function like storing data, storing instruction, storing address of the location in memory, and etc. The user registers can be used by an assembly language programmer for storing operands, intermediate result, etc. Accumulator or ACC is the main registers in the ALU and contains one of the operands of an operation to be performed in the ALU. We have memory. In memory, attached to the CPU is used for storage of data instructions and is called internal memory. The internal memory is divided into many storage locations, each of which can store data or instructions. Output unit. The output unit consists of output devices that are attached with the computer. It converts the binary data coming from CPU to human understandable form. The common output devices are monitor, printer, platter, flash, and so on. SAP1 or simple as possible on introduction. SAP1 is the first stage in the evolution towards modern computers. The main purpose of SAP is to introduce all the crucial ideas behind computer operations. Being a simple computer, SAP1 also covers many advanced concepts. SAP1 is a bus or organized computer. All registers are connected to the W bus with the help of tri-state buffers. In this block diagram, simple as possible, you have program counter, input and MAR 16 by 8 RAM, instruction, register, controller, sequencer, accumulator A, other subtractor, register B, output register, binary display. This is the flow of the diagram of this simple as possible. Main features. Simple as possible. One output device with 8 LEDs, a 16 bytes of read-only memory, 5 instructions, 3 with 1 operand, 2 with implicit operands. Accumulator architecture. Accumulator, B register, instruction register, or IR, out register, memory address register, or MAR. Architecture, 8-bit W bus, 4-bit program counter, only counts up. It starts counting from 0 and counts up to 15. 4-bit memory address register, 16-byte memory, 8-bit, 1-byte instruction register, 6-cycle controller with 12-bit micro instruction word, 8-bit accumulator, 8-bit B register, 8-bit adder and subtractor, lastly 8-bit output register. In this clock circuit, sample of logic circuit design. Program counter. Instructions to be executed are placed at the starting addresses of a memory. The first instruction of a program will be placed at binary address 0000. The second at address 0001. Now, to execute one instruction, first step is to generate the address at which this instruction is placed in memory. So this address is generated by 4-bit program counter that counts from 0000 to 1111 for a total of 16 memory locations. If the value of program counter is 0100, then the instruction at address at 4 will be executed next. Program counter is like a pointer register. It points to the address of next instruction to be executed. Here is the diagram or schematic of program counter. Input and memory address register or MAR. The MAR stores data 4-bit address of data instruction which are placed in memory. When SAP is running mode, the 4-bit address is generated by the program counter which is then stored into the MAR through the bus. This the okay, the RAM in initial design, the RAM is a 16 by 8 static titeller RAM. It means there are 16 memory locations from 0 to 15, and each location contains an 8 bit of data instruction. You can program the RAM by means of the switches to be used for address and data. Instruction register. When the instruction is placed at the value bus from memory, the instruction register stores this instruction on the next positive clock edge. The contents of the instruction register are split into two nibbles. The upper nibbles is a two-state output that goes directly to the block labeled controller sequencer. The lower nibble is a three-state output that is written onto the W bus when needed. This is the schematic of instruction register or how the instruction decoder. This is the adder and subtractor schematic diagram logic circuit. Stimulator. To add and sub to 8-bit numbers A and B, the accumulator register store the number A. It's the accumulator B register. To add and sub to 8-bit numbers A and B, the B register stored the number B. Supplies the number to be added or subtract from the contents of accumulator to the adder and subtractor. It's the B register out to adder and subtractors XOR gates. Output register. At the end of an arithmetic operation, the accumulator contains the word representing the answer. Binary display. The binary display is a row of 8 light emitting diodes or LEDs. Because each LED connects to one flip-flop of the output port, the binary displays show as the contents of the output port. This is the ring counter schematic diagram. From instruction register, instruction decoder, controller matrix. Now here is the table on how the program is in assembly. In address 0h content, but while in contents LDA 9h. This is an example of programming machine language. The 8080 and 8085 microprocessors. The 8080 was the first widely used microprocessor. The 72 instructions. The 8085 is an enhanced version of the 8080 with essentially the same instruction set. Both are designed by Intel Corp. Fetch cycle. The control unit is the key to a computer's automatic operation. The control unit generates the control words that fetch and execute each instruction. Ring counter. Successive clock pulses produce ring words of t equals 0, 0, 0, 0, 0, 1, 0 equals t2. Microinstruction. The controller or sequencer sends out control words during each t-state or clock cycle. The macro instruction. The instructions we have been programming with LDA add and sub are sometimes called macro instructions to distinguish them from micro instructions. Uh, in this figure of SAP1 is the simulation of program. Program counter. Yan po. Sa balik-balik lang po sila. Output. Pupunta dito sa input. Yan. In this last picture of simple as possible computer schematic diagram